Okay, let's talk about inverse transforms. So first, let's go through all of the basic ones, and I think the best way to learn these is to know the regular Laplace transform, and then just think backwards so that you can get the inverse. So our first one is one that's very popular. It's simply the Laplace transform of 1. And so this is equal to 1 over s. So the Laplace takes 1 and sends it to 1 over s. Therefore, the inverse Laplace transform takes 1 over s and sends it back to 1. So really nice, really simple. That's our first really important formula. The next one says if you have the Laplace transform of t to the n, this is going to be n factorial, and it's always 1 higher on the bottom. So it's s to the n plus 1. Now, most books say that this formula is valid for n equals 1, 2, 3, etc. It is valid for n equals 0. In fact, if n is 0, you're up to this case here. T to the 0 is 1, 0 factorial is 1, and here you would get s to the 0 plus 1, so you get s. So when n is 0, this formula reduces to formula 1. So I'm going to go ahead and extend what's usually found in textbooks, or rather just include something that's omitted. It's valid for n equals 0, 1, 2, 3, etc. Actually, let me just go ahead and write the 2 there for clarity. So 2, 3, there we go. A little more clear. So as far as inverses, this means that the inverse Laplace of n factorial over s to the n plus 1, this is equal to t to the n. And I really think it's instructive to go through this on your own and recreate these. Just write down the familiar formulas that you know for the Laplace transform, and then try to find the inverse transform using, backwards thinking. The next one I want to show you is the Laplace of e to the at. This is equal to 1 over s minus a. So going backwards, the inverse Laplace of 1 over s minus a is going to be e to the at. So really nice when you have these in a nice way like this, where you can practice your formulas, and then thinking backwards, I think, is really helpful. So all that's left is the sines and cosines and the sinches and cosinches. I want to emphasize that some textbooks, whether they be math books or engineering books, they often include extra formulas. I'm including somewhat the bare minimum, and we'll have to grind through some of the harder examples ourselves. So let's look at the Laplace transform of the sine of kt. The sine has the k, so this one is k over s squared plus k squared. And then, so the inverse Laplace here, I'm going to write it below because I'm make sure you can see it. The inverse Laplace of k over s squared plus k squared is just going to give us sine kt. These are very useful, by the way. The reason you need these, I probably should have mentioned this, is later on we'll have a differential equation, and we'll take the Laplace transform of the entire equation on both sides. We'll solve for the Laplace of the function, and then we'll find the inverse Laplace to undo that to retrieve the solution to the differential equation. That didn't make sense. It's okay. It probably wouldn't, but that's what we're going to do. We're basically going to use these to solve initial value problems. The Laplace of cosine kt. So I have a really weird way of memorizing this. Cosine has the s, so this is s over s squared plus k squared. So then the inverse Laplace of this is going to be, let's see, s over s squared plus k squared. Let's think about it. The Laplace takes cosine, sends it to this expression here. So the inverse Laplace takes this rational function and sends it back to the cosine of kt. Pretty cool. All right, so now we're going to go to the hyperbolics, and the hyperbolic formulas are the same, except there's a minus, which is kind of interesting, right? Because you can use sine and cosine to parameterize a circle, right? And a circle, the formula is, what is it? X squared plus y squared equals r squared. That's for a circle centered at the origin of radius r. We're not even talking about circles here, but just note that there's a plus here. And the hyperbolic ones can be used to parameterize a hyperbola. And the formula there has a minus. Kind of just a random, interesting observation that I wanted to make, but probably not something that's going to affect your performance on Laplace transforms. So let's do this one. The Laplace of, sinh kt. So just like sine has the k, sinh has the k. So this is k over s squared minus k squared. So the inverse Laplace of k over s squared minus k squared. This is equal to sinh kt. Sinh kt. And the very last one we're going to look at is the Laplace transform of the cosinh of kt. And so this one, remember cosine has the s. Let me just show you up here. Cosine has the s. So cosinh also has the s, right? So it's s over. And you might be wondering, I don't really need to memorize these because I have a formula sheet, which often is the case. Oftentimes in colleges, especially like engineering classes and stuff, even math classes, formulas for these are given. And so students typically have the formulas. However, you want to be really good at this. And in order to get really good at this, you have to know the formulas. So you end up memorizing them. So let's just do some examples. So I'm going to switch colors here. Start off simple. See if I have some examples here. Yeah, here's a really easy one. Let's do just an easy one here. Inverse Laplace of 1 over s to the, let's see what this says, 5. I could have made that up. Wasn't that enlightening? So let me write down the formula here for you. So recall that the formula for the inverse Laplace of n factorial over s to the n plus 1. This is going to be t to the n, right? This is the formula we're going to use in this problem. So inverse Laplace transforms are a little bit, they require a little bit more finesse than regular Laplace transforms. So I'm going to go ahead and write it down here again. So inverse Laplace. And we need to make it match this form here. So what do we have? We have an s to the 5. That's on the bottom. It's always one higher on the bottom. You see how there's an n factorial here? And here there's an n plus 1. It's one higher on the bottom. So if this is a 5, up here we need a 4 factorial. So I'm just going to put it there because we can do whatever we want, right? As long as we fix it later. So if I put a 4 factorial here, I have to divide by 4 factorial. So one clever way to do that is to multiply by 1 over 4 factorial like this. Right? It's a nice way to do it. So you basically write down what you want and then you fix it later. And now the 1 over 4 factorial, well, we know that's 1 over 24, right? 1 over 24 times, and then this piece here, right? This piece here, this is t to the 4th from the formula. And so that would be the inverse Laplace transform in this case. Hi everyone, in this video we have to find the inverse Laplace of this expression. So because we have a number up top and we have an s squared plus a number, it's very likely we're going to use the formula that leads us to the sine function. So recall that the inverse Laplace of k over s squared plus k squared, that's simply equal to sine kt. If you have an s here, just remember cosine has the s and that gives you cosine. So if you had an s here, you'd get cosine. But because we have a number, we're going to get sine. So we're almost there in this problem. If you look here, you have the 24. That's got to be the k squared. So the trick is to rewrite the 24 in a way that it matches k squared. So it's s squared plus, well, I'm just thinking square root of 24 squared. Because if you square the square root of 24, you're going to get 24. So then we need to have a k up here also. That's the thing, see? So what we do is we can just put it there because we can do whatever we want as long as we make it better. So I'm just going to put it there. And then the 6, you can pull it out. And then to get rid of this square root of 24, I'm going to put it here.
Boom, there it is. So again, we decided to just rewrite the 24 as the square root of 24 squared. We put this here, but when we put it here, we got to take it away. You see they cancel. And the 6 just came out. So all of this here is going to give us a sine function. So this is 6 over the square root of 24 sine of kt. But k is the square root of 24. So it's the square root of 24 times t. And let's just go ahead and leave our answer like that. You could probably reduce the square root of 24 and simplify a little bit, but let's just leave it. I hope this video has been helpful to anyone out there who is working on inverse Laplace transforms. Take care.
In this example, we're going to find the inverse Laplace transform of s plus 2 squared over s cubed solution. So to do this, we'll start by expanding the numerator. So we have the inverse Laplace transform of, and there's a formula we can use to expand the s plus 2 squared. Basically, you square the first one, so s squared. You multiply these two and you double it. So 2s times 2 is 4s. And then you square the last one, so 4. That always works whenever you have something like this, something plus something squared. The formula is a plus b squared. A is the first one, so you square the first one. You multiply them and double them, so 2ab. And you square the last one, so b squared. And this is all over s cubed. All right, and we're going to use the fact that the inverse Laplace transform is linear. So we're going to break this up into 3 different inverse Laplace transforms. First, let's break up this fraction though. So this is the inverse Laplace of, so s squared over s cubed. Very nice. Plus 4s over s cubed. Plus 4 over s cubed. All right. So now we can clean it up. And again, we can break it up into 3 inverse Laplace transforms. And since it's linear, we can also pull out constants. So let's see, s squared over s cubed. That's going to give us the inverse Laplace of 1 over s. Really nice. Plus 4 inverse Laplace. S over s cubed is 1 over s squared. Then plus 4 inverse Laplace 1 over s cubed. All right, so let me refresh your memory on some of the formulas we're going to use in this problem. So first of all, this one is just going to be 1 because the Laplace of 1 is 1 over s. So the inverse Laplace takes 1 over s and sends it back to 1. So that's pretty easy. Plus 4 times, and so to figure out this one, recall that the inverse Laplace of n factorial over s to the n plus 1, this is actually equal to t to the n. So here, it's 1 higher on the bottom. If you think of this as 1 factorial, okay, over s squared, it's 1 higher, so it's t to the 1. This is just t. Okay. Here, we have 1 over s cubed. Remember, it's 1 higher on the bottom, so we need a 2 factorial here. I'm just going to put it there in yellow, so I'm forcing it there as a 2 factorial. But if you put it there, you got to take it away. We'll divide by it out here. So this is going to be plus 4 over 2 factorial is 4 over 2, which is 2, times, and again, applying this formula, going to be t to the n here is 2, so this is t squared. The final answer is 2t squared plus 4t plus 1. Pretty decent example.
Hi everyone, in this video we have to find the inverse Laplace transform of this expression here. So because we have an s squared on the bottom and we have an s up here, that should draw us to use the formula that involves the cosine function. Recall that the inverse Laplace transform of s over s squared plus k squared is equal to the cosine of kt. The way I memorize this formula is I always just remember that cosine has the s, and then sine has the k. If there's a k here, this becomes the sine function. So just remember cosine has the s. Okay, so there's no number up here. So maybe we can pull out the 4 up here. So let's do that. So 4 inverse Laplace. And so when we do that, we're left with an s up top. Also, there's no coefficient here on the s in this formula, so we need to pull the 4 out from the bottom. So when you pull that 4 out from the bottom, you're going to get s squared plus, and then pulling out a 4 from the 1 is going to give you 1/4. That's the clever step. And you can check this by working backwards. 4 times s squared is 4s squared. 4 times 1/4 is 1. So everything is 100% awesome. So this is going to cancel. So this is the inverse Laplace transform of s over s squared. Now you can rewrite your 1/4 as k squared. That's going to be 1/2 squared. Beautifulness. And the cosine function has the s. So this is going to be cosine of kt, but k is 1/2. And that is the final answer. I hope this video has been helpful. Take care. Hi everyone, in this video we're going to find the inverse Laplace of this expression. We're going to do it using partial fractions. So let's go through it. So first thing you do is you take this expression and you write it down. And I believe we can factor out an s here. So this will be s parentheses s squared plus 2. Yep, looks like I did that right. So whenever it's linear, you just put a constant. So a over s. And then whenever you have like something squared plus a number, you have to have a linear piece up top, like this, bs plus c over s squared plus 2. Just remember, if you ever did this before, you probably did it with x. So if you had like 2x squared plus 1, x squared plus 7, you would write this as ax plus b, x squared plus 1, plus cx plus d, x squared plus 7. So that's how it works in the past. You've probably seen this before with just regular x's. Here we have s. It's exactly the same thing. So we had s squared plus 2, so we had to have that bs plus c. If I throw a piece here like x minus 4 on top, that would just be e over x minus 4, because that's linear. It's to the first power, right? So the s is linear. Okay, just wanted to make sure that you got that. So the next step in the partial fraction process is to multiply both sides by this. So we're going to multiply by s squared plus 2, and then we're going to do it here as well. So s squared plus 2. So when you do it here, this all goes away. So you just get 1 equals. So a over s is being multiplied by this. So the s's will cancel. So you're left with a parentheses s squared plus 2. Then over here, these will cancel, so you're left with plus bs plus c times s. Okay, so when you get to this step, there's an order to do things so that it's most efficient. And that order is the following. You always ask yourself, what can you plug in that will make things go away such that you'll get an answer? Like, if there's anything you can plug in that will give you an answer, you want to do that first. After you've exhausted all your possibilities, then you go to equating coefficients. If you do things in that order, it'll always be easier. So what can we plug in that will give us an answer? Well, s equals 0. If we plug in s equals 0, we'll be able to get a. So let's do that. So if you set s equal to 0, you get 1 equals. So this vanishes. It's all 0. It's all gone. So we get 0 plus 2, so we just get 2a. Oh, that's so beautiful. Look at that. So a is equal to 1 over 2. That's it right there. Perfect. So now what I'm going to do is I'm going to do this. I'm going to put a 1/2 here. Right? We can do whatever we want. So there it is. So now there's nothing else we can plug in to find b and c right away. You could plug in like 5 and 7, and you would get 2 equations with 2 variables, and you could solve them. But that's not very pretty. So now we're going to equate coefficients, because there's nothing else that we can plug in that will immediately give us one of the variables. Oh, I probably should mention this. If you can use the cover-up method, you do that. If you can't, that's doesn't work here. If you can't use the cover-up method, then you do partial fractions, and this is the best way to do it. So plug stuff in until you're out of options. We're out of options. There's nothing we can plug in that will give us B or C right away. Then we resort to equating coefficients. So how does that work? Well, you start with your highest power of S, which is S squared. That's a good place to start. On the left-hand side, we ask ourselves, what is the coefficient of S squared? Well, 0, right? There's a 0 S squared here. It's really there. So 0. On the right-hand side, we have 1/2 times all this. So 1/2 is one of the coefficients of S squared. And then B S squared. We have BS times S. That's BS squared. Oh, that's beautiful, isn't it? Look. So 1/2 S squared. So 1/2 BS squared. So B. So now we just solve for B. So B is equal to negative 1/2. That's how pros do it. Now let's go to the S terms. So S terms, what does this angle bracket mean? Absolutely nothing, I just made it up. So 0, there's really a 0S here. So 0 is the coefficient of S on the left-hand side. There's no S's here. The BS is not going to give us an S. Oh, the C will give us an S, right? CS. Oh, look at that. C is equal to 0. So good. I love these problems. Okay, so now we can rewrite what we have. So going back to what we have. So A over S, A was 1/2, so we can put the 1/2 in the front. And B is negative 1/2, so and the C is 0, so it'll be negative 1/2 S squared plus 2. So now we're going to find the inverse Laplace of this. So inverse Laplace is linear, so we can just take the inverse Laplace of each piece. So we have this. This is so beautiful. Minus 1/2 inverse Laplace. I love Laplace transforms. It's L for love. No, it's L for Laplace, not love. This is the square root of 2 squared. Right, you want to write 2 as a number squared. Why? Because remember, this has an S, and cosine has the S. That's your K. The inverse Laplace of 1 over S is 1. So we just get 1/2 minus 1/2. This is a cosine. Your K is the square root of 2. So square root of 2, T. And that would be the final answer. Let me remind you that this is just one. It's a formula. And this one, if you're curious, if you don't know anything about Laplace transforms and you're watching this video, this formula, usually by the time you get to these problems, you have most of these formulas memorized. But just in case you don't, that's it right there. So I hope this video has been helpful. Take care. In this video, we're going to find the inverse Laplace transform of this expression. So to do this, we're going to use partial fraction decomposition. So we'll start by writing down what's inside the inverse Laplace. So we have 1 over S squared plus 1, then times S squared plus 16. So S squared plus 16. So whenever you have quadratics, you have to have AS plus B. Then on the bottom, we have S squared plus 1. And then this one will give us CS plus D. So plus CS plus D. And then here we have S squared plus 16. So if it was like S plus 1, it would be linear. In that case, you would just have an A. But whenever it's S squared plus a number, you have to have the AS plus B. The next step is to clear the fractions. So to do that, we're going to multiply both sides by whatever's on the bottom here. So I'm going to multiply both sides by S squared plus 1, S squared plus 16. I'll just put it up here as a reference. So this is being multiplied by this. That's going to give us 1. Then over here, we're going to multiply all of this by the same thing. So S squared plus 1, S squared plus 16. Now you could do it in your head, but I like to show this. That way it's easier to not mess up. So we're taking this and we're multiplying it by all of this. So these cancel, so we're left with AS plus B. So AS plus B. And then times the S squared plus 16, that's what's left. So S squared plus 16. Then plus this times this. So now the S squared plus 16's cancel, so we have CS plus D times, and then S squared plus 1, because these cancel. Okay, when you get to this point in the problem, you should always ask yourself, is there anything you can plug in right away that's going to give you one of the answers? In this case, no, right? There's nothing you can plug in that will give you A, B, C, or D. So then you resort to what's called equating coefficients. So let's go ahead and do that. So to equate coefficients, you start with the highest degree terms. Let's start with s cubed, because that's the highest degree terms. So s cubed. So on the left-hand side, there is no s cubed, or is there? There's really a 0 s cubed. So the coefficient of s cubed on the left-hand side is 0. So 0. And then on the right-hand side, the way it works is you have to pick exactly one from each parentheses. So how can we get an as cubed from this first grouping? Let's see, we can pick the as and we can pick the s squared. Yep, as cubed. So that's going to be a, because as and s squared is as cubed. And then over here, yep, cs cubed. So a plus c equals 0. So now we go to s squared, so I'll write it here. So again, it's going to be 0 s squared over here. That's the coefficient of s squared on the right-hand side. So 0 equals, let's see, can we use the as to get an s squared term? No, we can't, right? Because if you pick this one, you have to pick one of these, and you're not going to get an s squared. But we can use the b, right? bs squared. So b. Likewise here, we can use d, ds squared. Just keep going down the line. Now we go to s. So s terms. So again, there's no s terms here. You can think of it as 0s plus 1. So 0. Let's see, I think here we can use the as. As and 16, that's going to give us 16 as. So 16a, and there's nothing else there. And here it's going to be cs. So just c, right? S times 1 is cs, so the coefficient is c. Okay, now we're down to the constant terms. I'll just put C-O-N-S-T-A-N-T. I'll spell it. I'm just gonna abbreviate, but why not just go ahead and spell it? So the constant term is 1. So 1. And let's see, I guess it's gonna be the 16 and the b in this case. That's, you pick the b, you pick the 16, you're multiplying. So you get 16b. And then here you're gonna get big D, so plus d. Okay, so we have 4 equations with 4 variables. Now we can solve them. This is pretty convenient. If you subtract these, you get 0 minus 0, so you get 0. A minus 16a is minus 15a, right, subtracting. A minus 16a is minus 15a. C minus c is 0, so that goes away. So we just get a equals 0. Right, c minus c is 0, so we just divide by 15. By negative 15, we get a equals 0. I'm going to put that in a box. Well, if a is 0 and you plug it in here, that means c is also 0. So c equals 0 in this, as well in this case. To solve this system of equations, we can do the same thing. We can subtract. Let's see, 0 minus 1 is negative 1 equals b minus 16b is minus 15b. And then d minus d is 0, so we just get 0. Divide by negative 15, so we get b equals 1 over 15. That's how pros do it. Again, 0 minus 1 is negative 1. b minus 16b is negative 15b. d minus d is 0. Divide by negative 15, we're here. Plug this in here. And then so that would give you d equals negative 1 over 15. You can convince yourself of that because you would get 0 equals 1 over 15 plus d. I'll write it. 1 over 15 plus d. And that's equal to 0, so you subtract and you get a negative. All right, we're good. Now all we have to do is plug everything back into the original and find the inverse Laplace. I'm going to go ahead and erase this, and I'll do it up here. So let's see, A and C are 0, so we have B is 1/15, so I'm going to pull that out. So this is gone, so B is 1/15, so I'll put it in the front. So 1/15 inverse Laplace transform of 1 over s squared plus 1. Right, because the a is 0 and the b is 1 over 15, and we put that in the front. And then we have d is negative 1 over 15, and c is 0. So basically, we're going to pull this out. So this is 0, negative 1 over 15, so pull out the negative 1 over 15. Inverse Laplace. And we have 1 over s squared plus 16. Think of 16 as 4 squared. And think of 1 as 1 squared. And the reason we want to do that is because now we're going to use the formula for sine. Recall that the inverse Laplace of k over s squared plus k squared, this is equal to sine kt. If you have an s here, just remember cosine has the s, sine has the k, and you'll be able to do this all day long forever. So this is going to be 1/15. Looks like k here is 1, so it'll be sine t. Beautiful stuff. Minus 1/15. It looks like k here, oh, look at this, look at this. There is a 4 here, that's your k, but there's not a 4 here. So here's what we do. We can do whatever we want as long as we make it better. So I'm going to put a 4 here. You easily can't do that. Well, yes, we can. We can just take it away by putting it there. So this will actually become 1/60. You see how they cancel. Boom, boom, they're gone. Same thing. And now this will be sine of 4t. And that is how pros do it. I hope this video, that's a 60. Let me fix that. 60. I hope this video has been helpful to anyone out there who's working on Laplace transforms. Take care. In this video, we're going to find the inverse Laplace of this expression here. So this looks like we're going to use partial fractions. It looks pretty complicated. So let's go ahead and write it over here and try to use partial fractions. So we have 4s minus 8 over. You notice you can pull out a 4 too. I didn't do that, but so I don't think it's necessary. Here you can pull out an s. So we have s plus 1. And then here we have s squared plus 1. Good stuff. So when you use partial fractions, if it's linear, you just put like a constant, like an a. And if it's like quadratic, you have to have like as plus b. So here it's s, so it's just a over s, plus. Here it's s plus 1, so it's b over s plus 1. And then here it's s squared plus 1, so you have to have cs plus d. Remember, whenever it's a quadratic, you have to have that, like the ax plus b, except here it's not x, it's s. So the next step in partial fraction decomposition is to eliminate the fractions. So what you do is you multiply both sides by whatever is here on the bottom. So it's s plus 1, s squared plus 1. We do the same thing over here, okay? So we have s plus 1, s squared plus 1. So this cancels over here. All of these cancel, so you're left with 4s minus 8 equals, and let's see, we have all of this times this. So it looks like the s will cancel, so we're left with a s plus 1, and then s squared plus 1. Yep, looks good. Plus b, and then we cancel the s plus 1, so we have s squared plus 1. So s squared plus 1. And then we cancel these, so we have cs plus d, and then looks like we have s plus 1. Yikes, let me check that because I did that really, really quick. So we have this times this, so the s's cancel, so we're left with this and this. Yep, it looks okay. We have this times this, s plus 1's cancel, we're left with this and this. Yep, looks okay. We have this times this, the quadratic cancels, we're left with s plus 1. We're okay. So the next step in partial fraction decomposition is to ask yourself, is there anything I can plug in that will make things go away? In other words, is there anything you can plug in that will immediately give you one of the variables? Well, there's two numbers that will do that. 0, because it'll make all of this will go away, and you'll get a. And also negative 1, because this will go away, and this will go away, and you'll get b. So let's go ahead and do that. Let's plug in what we can to get some answers. So s equals 0. Let's do that one first. So plugging in 0 for s, we're going to get 0 minus 8. So we just get minus 8. And then plugging 0 for s, this is 0 and this is 0, so it's going to be a. Okay, so a. And, oh, this goes away at 0, this goes away at 0. Oh, look at that. That's a. So that's an accomplishment. That was pretty cool. I mean, I guess I knew it would happen, but I wasn't really thinking about it that much. I just knew stuff would go away, and yeah, it goes away, and it worked out really nice. Let's do negative 1 now. It's always fun when things work out nice. So plugging in negative 1 here, we get negative 4 minus 8, so that's going to be negative 12. This will go away because the whole thing is 0, right? Negative 1 plus 1 is 0. The whole thing vanishes. This goes away too. So we just get b negative 1. And then negative 1 squared is 1. So 1 plus 1 is 2. So you get negative 2b. So that means b is equal to 6. So b is equal to 6. So now what I'm going to do is I'm going to be cheap. I'm going to do this. I'm going to put a 6 here. I'm going to do this, and I put a negative 8 here. All right, so now there's nothing else we can plug in that will immediately give us an answer. So you could plug in like 17 and 20, not a good idea, and you would get two equations with two unknown variables, namely C and D, and then you could solve them. So that's a thing. You can always just plug in numbers and get equations. But always try to do this first. So now when you get to the point where you can't do this anymore, now is when you go to the method of what's called equating coefficients. So we're going to look at the highest degree terms. I think those are going to be s cubed terms, see? So let's look at the s cubed terms. So on the left-hand side, we're looking for the coefficient of s cubed. Well, there is no s cubed there, so the coefficient of s cubed is 0. There's really a 0 s cubed there, so it's just 0. Right, because it's really there, but it's not. So the coefficient of s would be 4, and the constant would be -8. But the coefficient of s cubed, or s squared, or rest of the 20th power, they're not there, so they're just 0. So now we need to figure out how to get s cubed from all of this. And so the way it works is, in order to multiply stuff, you have to pick one from each parentheses. So we have to take the -8. And can we get an s cubed here? We can, right? -8s cubed. So pick the s, pick the s squared. So pick one, pick one, pick one. So -8s cubed gives us -8. What about here? Oh, yep, we can. Plus 6s cubed. So plus 6. And what about here? Let's see, can we use the c? Yes, yes we can. We can take the c, take the s, take the s. So plus c. So this one, and this one gives us c. Can we use the d? ds squared. Nope, fails. So we have, I'm going to use an implication arrow here, 0 equals -2 plus c. So c is equal to 2. That gives us c equals 2. Okay, so now we're just going to go down the line. Let's go to s squared terms. So s squared terms. This is a harder problem. So again, on the left-hand side, there is no s squared, so I'm just going to put it there to show you the coefficient is 0. Over here, let's see, we have to pick the -8. Can we use the s to get an s squared? No, we can't, because if I pick the s, I have to pick one of these. This will give me a cube, this will give me an s, so no good. I think we can use the 1. -8 times 1 times s squared. Yep, -8s squared. That'll work. What about here? I don't think we can get an s squared here, because you have to take the 6 and the s, and there's no way to get an s squared, because you would get a cubed or just an s. What about here? Can we use the c? Let's see, cs squared and the 1. See that? That's really clever. cs squared, so plus c. Oh, we know what c is. C is 2. I'll put the c, but c is 2. So this is a 2. So cs squared. Now can we use the d? I think we can. Check it out. Look, ds squared. So c is 2, so you get 0 equals -8 plus 2 plus d. So that means we have 0 equals -6 plus d. So that means that d is equal to 6. Boom. We have all of them. Now we're just going to plug them in and figure out this monstrous problem. Okay, so I'm going to erase this and just plug everything in. This is exciting. So we have so inverse Laplace. So what is a? A is -8. That's going to be easy. So -8 over s. Let's go ahead and write it out. When you find the inverse Laplace of 1 over s, you're just going to get 1. So it's good to talk about it. B is 6. So it'll be plus 6 over s plus 1. That's going to be an exponential. So remember, if it's 1 over s minus a, it gives you e to the at. So it's s minus -1. This is going to give us an e to the -t. C is 2. So plus 2c, and then d is 6. Ooh, this is harder. Oh, sorry. So c is 2. So 2s plus 6. Yeah, because c is 2 and d is 6. Well, this is no joke, and this is s squared plus 1. So we are here. Okay, so now we have to carefully break everything up. So everything looks okay. Our c is 2, our d is s. Let's finish this thing. So now we'll break it up into 4 pieces. So I'll pull out the -8. So we have inverse Laplace of 1 over s. Okay, I'm going to go ahead and erase the rest of the board. Keep it clean. Pull out the 6 here. So plus 6. Inverse Laplace, 1 over s plus 1. Kind of a fun problem. I'm going to break this up into 2 different Laplace transforms. It's 2s over this. So I'll pull out the 2. And then we have s over s squared plus 1. Pull out the 6, inverse Laplace. What a nice problem. I think this is a really good example of like partial fractions because you have the linear terms and you have the quadratic terms and you have plugging in numbers and you have equating coefficients. It's like the ultimate problem. So I just broke it up this over this and then this over this. I just pulled up the 6 and the 2. Okay, this is 1 over s from the formulas. So it's just 1 rather. So this is just 1. This is 1. This one is e to the negative t. That's a formula, right? The inverse Laplace, I'll write it. Inverse Laplace of 1 over s minus a is e to the at. And again, the inverse Laplace of 1 over s is just 1. It's a formula. This one is a cosine. This is 2 cosine t. How do I know that? Cosine has the s. The inverse Laplace of s over s squared plus k squared is equal to cosine kt. Just memorize it as cosine has the s, and you'll get it every time, plus 6. And this one is a sine. Sine has the k. So if I put a k here, this becomes sine kt. So k is 1. So this is 6 sine t. And that, my friends, is the inverse Laplace transform. This problem was tough. This is harder than some of the differential equations that we solve. Definitely a little bit more challenging than some of the other problems. I hope this video has made sense and hopefully it's helped. So take care. Hi everyone, in this video we're going to find the inverse Laplace of this expression here. So we'll start off by rewriting what's inside here. So we have s over, and then let's think. If this factors, we should factor it. If it doesn't factor, then the next best strategy would be to complete the square. I think it's going to factor. Let's try it. So this is s. If it doesn't factor and like I messed up and we'll complete the square. I think 3 and 1. Yep. And I think the 3 is positive and the 1 is negative. Let's check. So s times s is s squared. Negative 1 times 3 is negative 3. The inside piece is negative s. The outside piece is 3s. Negative s plus 3s is 2s. So it does indeed factor. So now we're going to use partial fractions. We can write this as a over s minus 1 plus b over s plus 3. That's because these are distinct linear factors. Okay, we can use the cover-up method to find a and b. So whenever you have distinct linear factors like this, you can use what's called the Heaviside cover-up method. It's named after Oliver Heaviside. This is the same Heaviside after which the unit step function is named, actually. Okay, so a is equal to, so to find a, you cover up what's under a, so s minus 1. And you say, okay, what makes this piece 0? So 1. So if I put a 1 here, it's going to make this bottom piece 0. So you put a 1 everywhere else over here. So it'll be 1 over 1 plus 3. So 1 over 1 plus 3. So that's 1 over 4. So that would be your a. So a is equal to 1/4. Okay, to find b, you cover up what's under b. So b, you just go over here and cover up the s plus 3. And you ask yourself, what makes that undefined? So negative 3. So you plug in negative 3's into these s's over here. So it'd be negative 3 over negative 3 minus 1. So this is negative 3 over negative 4. This is equal to 3/4. So that's b. So you can write this. A is 1/4. You put it up top, but you really put it in the front when you do this. So 1/4 times 1 over s minus 1. And then b, same thing. You put the 3/4 in the front. 1 over s plus 3. Good stuff. Okay, now we just have to take the inverse Laplace of this. So when we do that, we can pull out the constants because the inverse Laplace is linear. So I'll actually show all the work. This is the inverse Laplace of 1/4, 1 over s minus 1, plus 3/4, 1 over s plus 3. And then we can break it up into 2 individual inverse Laplaces. This is 1/4 inverse Laplace of 1 over s minus 1, plus 3/4 inverse Laplace, 1 over s plus 3. All right, good stuff. So now we just use the formula on both of these. This is equal to 1/4. So 1 over s minus 1, that's going to give us e to the t. And then here, this is 3/4. This is going to give us e to the negative 3t. How do I know that? There is a formula, right? If you have the inverse Laplace of 1 over s minus a, that's equal to e to the at. So in this first example here, a is 1. So you simply get e to the t. Here it's s minus negative 3, so that gives you e to the negative 3t. I hope this video has been helpful. Take care. Hi everyone, in this video we're going to find the inverse Laplace transform of this expression, 1 over s squared plus 3s. So to do this we're going to use partial fractions and we're going to use the cover-up method. So the first thing we'll do is rewrite the inside piece. You can factor out an s. That's the first thing you can do here. Notice s times s is s squared, s times 3 is 3s. Okay, so this is equal to a over s plus b over s plus 3. That's the technique for partial fractions. Whenever these are linear and they're distinct, you do that. So this is to the first power, this is to the first power, so you just put a letter there. Okay, so how do you use the cover-up method? This is the key. So to find a, what you do is you cover up what's under a. So s is under a. And then you ask yourself, what makes that 0? Well, 0, right? 0 makes this piece undefined. So you plug in a 0 here. So 1 over 0 plus 3. So a is 1/3. I'm going to put that in a box. Again, you look at what's under s, you cover it up, and you say, what makes that undefined? What makes the bottom 0? 0, and then you just put it here. Let's find b. Maybe it'll make a little more sense. To find b, you cover up what's under b. And you say, okay, what makes that 0? What makes this fraction undefined? Well, negative 3. So you put a negative 3 over here, 1 over negative 3. And that gives you negative 1/3. So again, to find a, you cover up what's under a, you plug in whatever makes the fraction undefined, so that's 0, 1 over 0 plus 3, there it is. To find b, you cover up whatever under b, and you say what makes this fraction undefined, what makes the bottom 0, negative 3, so 1 over negative 3. So we can rewrite this. Now these numbers, it's 1/3 over s. Human beings don't do that, they usually put it in the front like this. Boom! Same thing, right? If I have 1/3 divided by s, it's the same as this. Same thing, because you would get 1/3 times the reciprocal of s, which is the same thing, right? The reciprocal of s is 1 over s, because it's really s over 1. So life is good. This one comes out this way, so minus 1/3 times 1 over s plus 3. All right, good stuff. Now we're ready to take the inverse Laplace of this beast. So when you're taking inverse Laplace transforms, remember it's linear, so you can pull all these constants out. So you can just work with each individual piece. So it'll be 1/3 inverse Laplace of 1 over s minus 1/3 inverse Laplace of 1 over s plus 3. So this is equal to 1. Just from memory, right? The Laplace of 1 is 1 over s. Recall that formula from the past. So the inverse Laplace of 1 over s is 1. So this is 1/3 times 1, which I won't write, minus 1/3. So formula for this one, this is going to be an e. Recall that if you have the Laplace of e to the at, that's simply 1 over s minus a. So the inverse Laplace of 1 over s minus a is e to the at. Here it's really s minus negative 3, so your a is negative 3, so it's e to the negative 3t. And that, my friends, would be the final answer. This is a really nice question because it involves the partial fractions and the cover-up method. I hope this video has been helpful. Take care. In this video, we're going to solve this differential equation using Laplace transforms. So in the method of Laplace transforms, the first thing you do is you take the Laplace of both sides of the dE. So let's go ahead and do that. Start off by taking the Laplace of y double prime plus y, and that's equal to the Laplace of all of this. So the Laplace of the square root of 2 sine square root of 2t. So you could have skipped this step by distributing the Laplace through because it's linear. Likewise, I could have pulled out the square root of 2. But I wanted to show all the steps. So the very first step is basically apply the Laplace transform to both sides of the differential equation. Then you can use the fact it's linear. So it'll be the Laplace of y double prime plus the Laplace of y. And then that's from linearity. Likewise, we can pull out this constant. So this is the square root of 2 Laplace sine of the square root of 2 times t. And so we're here. So if I was doing this and I wasn't making a video, I would have started with this step here. So you can just jump into this step. So now we have to use the formulas. There's multiple formulas. Let me refresh your memory in case you've never seen this before. So the first formula says that the Laplace of y is equal to psi of s. I call it pitchfork y. That's just what I call it. Then the second formula, which we don't need in this problem, but I'll write it anyways for completeness, is s pitchfork y of s minus y of 0. And the third formula that we often need is the one for the second derivative. That's going to be s squared pitchfork y of s minus s y of 0 minus y prime of 0. And I will be completely 100% honest. For me, I think, and for most people, these are extremely intimidating when you first see them. You think, oh my God, how am I ever going to memorize these formulas? The way I memorize it is, this is the first derivative, so it starts at the first power. This is the second derivative, so it starts at the second power. And it ends in one less derivative. So this ends at the 0th derivative. That's the first derivative, it ends at one less. This is the second derivative, it ends at one less. So that's how I do it. Let's go ahead and apply these formulas over here. So we have second derivative, so it's s squared pitchfork y of s minus s, and then notice it ends at the first derivative, so it must be y of 0 minus y prime of 0. Notice the powers count down too, s squared, s to the 1, s to the 0. And the derivatives count down going the other way. First derivative, 0th derivative, no derivative. So all kinds of memory tricks you can create in your mind to help yourself memorize it if you need to memorize it. Plus, this one's pitchfork y of s. This is equal to the square root of 2. The Laplace of sine of this, so recall, there's another formula that we're going to use here, so I'll refresh your memory. The Laplace of sine kt, this, just remember cosine has the s, sine has the k. So it's k over s squared plus k squared. Okay, so in this case, k is the square root of 2. So it's square root of 2. Oh, look at that. Square root of 2 times square root of 2 is 2. I did not know that would happen. I have not done this problem, by the way. So, and then this is s squared plus, and then when you square the square root of 2, you get 2. A happy day. So you get 2 over s squared plus 2. Kind of cool that that happened. That's, you know, it's probably on purpose. Whoever made this problem up decided, hey, let's put that there so when you multiply them, you get 2, right? Good stuff. Okay, all right, so I'm going to erase all of this, and let's just keep going. So again, we take the Laplace, we use those cryptic formulas. Now we use our initial conditions. So you use them early in the problem, which is very different from other differential equations. So y of 0 is 6, so this is s squared pitchfork y of s. Minus y of 0 is 6, so this is 6s. So 6s minus y prime of 0, which is 0. I'll write it, even though it's 0, just for completeness, plus our pitchfork y of s, and that's equal to 2 over s squared plus 2. So now what you do is you solve for pitchfork y. Okay, so we can factor out a pitchfork y here, so pitchfork y of s. This looks like it's going to get a little bit harder. This is s squared plus 1, right? That's looking at this one and at this one. And let's add this bad boy to the other side. This is 2 over s squared plus 2 plus 6s. So we're here. Okay, so I have a decision to make. Do I add these up or do I do them separately? I'm thinking. Let's see. So if we divide this by this, we're definitely going to have to use partial fractions, you know, in order to resolve this problem. Likewise, if I have 6s over s squared plus 1, that's also going to take some work. I think I'm going to add these up first and then divide by, no, let's do it separate. Let's do it separate. So pitchfork y of s will be 2 over, okay, 2 over, and it's going to be s squared plus 2 plus 6s over s squared plus 1. Yeah, this is pretty easy to do by itself, right? This is going to be a cosine, because remember, cosine has the s. Oh, I forgot something here. Really bad. What goes here? This would make it completely, I was like, wow, that looks easy. That's because we're missing this piece here. Okay. If that was gone, the problem would be very, very easy. Okay, so now what we have to do is we have to find the inverse Laplace of this, okay? So because this if you recall, this is the Laplace of y. So the Laplace takes y and gives you this. So the inverse Laplace takes this and gives you back y. Y is what we're looking for. We're trying to solve this differential equation, so we're looking for y. So the Laplace of y is equal to this, so the inverse Laplace of this is equal to y. So the inverse Laplace of this is the answer. So what makes a question easy or hard is this. You know, if this is hard to work with, then the question's hard. If this is easy, the question is easy. Let's go ahead and rewrite this over here, and then we'll work on the inverse Laplace of all of this. I'm going to erase all of this, okay, and rewrite it over here. So we have pitchfork y of s is equal to 2 over that. So we have 2 over s squared plus 2, s squared plus 1, plus, and then we have 6s over s squared plus 1. So again, this piece is easy. We can use a cosine for this. It's this piece here that causes problems. That's a 2. It's an ugly 2. So let's go ahead and use partial fractions on this piece here. So we have 2 over s squared plus 2, s squared plus 1. And so to use partial fractions on this, we are going to use the setup as follows. This is as plus b over s squared plus 2. That's because this is quadratic. If it was just like s, or like if it was just s plus 2, it would be a. But whenever it's like s squared plus a number, you have to have something like that. Plus, and then here we have cs plus d over s squared plus 1. Okay, so we're here. So now what we have to do is multiply both sides by this. Okay, so I'm going to do it mentally, but maybe I'll write it. S squared plus 2, s squared plus 1. That's what we're doing. And then same thing here. S squared plus 2, s squared plus 1. So these will cancel, so we'll just get 2 equals as plus b, so parentheses as plus b. And then the s squared plus 2 cancels, so we're left with s squared plus 1. So s squared plus 1 plus cs plus d. This problem is hardcore. Cs plus d. This will cancel, so we'll get s squared plus 2. So we're here. So now I'm going to erase this so that it's not like in the way. So that was just a note for ourselves so we can clarify our thinking. Whenever you get here, you always want to ask yourself, is there anything you can plug in that will give you one of the answers right away? And the answer is no, right? There's nothing you can plug in here that will give you one of the variables right away. So we're going to immediately go to equating coefficients, right? By the way, if you plug in 0, you'll get b and d, right? You won't get just b. So there's nothing you can really do to like find one of the letters. So let's go to equating coefficients. When we do that, we pick the highest power. So in this case, the highest power is 3. So let's look at the s cubed terms. So s cubed terms. So on the left-hand side, the coefficient of s cubed is 0. There's really an invisible 0 s cubed here. So it's 0. And let's see, how this works is, in order to find a term here, you must pick exactly one from each parentheses. So you have to pick one from here, and you have to pick one from here. So let's see, can we get an as cubed from this? Well, if we pick as, we can pick s squared, so that'll give us as cubed, as cubed. So a is the coefficient of as cubed that comes from these two terms. Here, it'll be cs cubed, so plus c. So that gives us our first equation. Okay, now let's go to s squared terms. Just go down the line. Again, there's really an invisible 0 s squared here. You could do this. And so the coefficient on the left-hand side is 0. Let's see, can we use a to get an s squared? No, we can't, right? So, because we can either get as cubed or as, so that doesn't work. What about b? Yes, we can, right? bs squared, so plus b. And then here we can use d. So that's good. So d. Right, we can't use c. Right, cs will give us a cubed or an s, so no good. Let's look at the s terms. I'm going to come over here. I don't know why I did it like that. S terms, same thing. You can have a 0s here, so 0. Looks like as times 1, so it'll be a. As times 1, so a. And then here, cs times 2, so 2c. So 2c. So 2c. Good stuff. And the last ones are the constant terms. So the constant terms, well, on the left-hand side, hurrah, it's no longer 0. 2 is the constant term. And here we're going to get b. Oh, that worked out really nice. I did not do this on purpose. You'll see. And then plus 2d. So I did not do this on purpose. This is a pure coincidence because I have not worked out this problem in months. But look, everything is lined up for us. That was not intentional. I'm feeling really good right now. So now we have 4 equations with 4 variables. So check this out. Let's subtract these. 0 minus 0 is 0 equals a minus a is 0. C minus 2c is negative c. Oh, that means c is equal to 0. But if you plug 0 back in here, that means a is equal to 0. So c and a are both equal to 0. So let me just write that up here. So in case you can't see it, I'm not sure if you can. So a and c are equal to 0. So we have that. So now we can do the same thing here. We can subtract. 0 minus 2 is negative 2. b minus b is 0. d minus 2d is negative d. Oh, look at that. So d equals 2. Because negative 2 is negative d. So then you plug it back in here, you get b plus 2 equals 0. So b plus 2 equals 0. So b is negative 2. Boom. That worked out really, really, really nice. Again, a minus a is 0. C minus 2c is negative c. So we get c equals 0. Plug it in here, you get a equals 0. And then subtracting these, you get 0, you get negative d, so you get d equals 2, plug it back in, you get b equals negative 2. Worked out really nice. So let's plug it back in here. Let's see what we got. So a is 0, so that's gone. So b is negative 2, so we get negative 2 over s squared plus 2. And then c was 0, so and then d is 2, right? d is 2. So this is plus 2 over s squared plus 1. So now we just got to find the inverse Laplace of this, and we got it. So I'm going to squeeze it in up here. So we can take the inverse Laplace of each piece, and we can pull out constants. So y is equal to negative 2 inverse Laplace of this piece. Okay. So this is really s squared plus the square root of 2 squared. You might say, what are you doing? I'm using formulas. Okay, I'm using formulas here. So this here, the formula we're going to use is this one. The inverse Laplace of k over s squared plus k squared is sine kt. Likewise, if you do this with an s, you get cosine kt. Remember, cosine has the s. So I'm running kind of messy. So I wrote this one down because we still have to add this piece as well at the end. So we have all of this plus this, and we're finding the inverse Laplace. So here we need a square root of 2. Because we want to make it match this formula, you see, so k. But when you put it there, you got to take it away, like that. And then here we pull out the 2, inverse Laplace. Okay, and then we have 1 over s squared plus 1 squared. So our k is 1 in this case. And then we have this piece here. So plus 6, inverse Laplace. I should have erased. Sorry. This is s over s squared plus 1. Okay, so what just happened? So we got here, and we decided to take the inverse Laplace of this as well as this, right? Because this is the same as this. So we take the inverse Laplace of this, and then this, and that will be y. So this top one here, this is going to be negative 2 over root 2 sine of kt, so square root of 2t. And this one will be plus 2, just sine t. And the last one is plus 6, and that's a cosine t. And this would be the solution to the DE coming from these 3 terms. I think the hard part is going through the partial fractions, but once you get here, it's not too bad. So again, once we got this piece is this piece. Okay, these are the same thing. And then so y is equal to the inverse Laplace of this plus the inverse Laplace of this. So the inverse Laplace of this is right, it's these two. And then this is the inverse Laplace of this. So then that is the final answer. I hope this video has been helpful. Got a little bit messy there at the end, but yeah, take care. In this video, I'm going to show you how to solve a differential equation using Laplace transforms. So let's just jump into it and go through it. And as we go through it, I'll show you the formulas that you need. So the very first step you need to do is take the Laplace transform of both sides. So we'll start by taking the Laplace of y double prime plus 5y prime plus 4y, and that's equal to the Laplace, I love that L, of 0. It's really beautiful. Okay, so the Laplace transform is linear. So what you can do now is take the Laplace of each individual piece. So this is the Laplace, Laplace of y double prime, plus 5 Laplace of y prime, plus 4 Laplace of y. It's a lot of L's. And the Laplace of 0 is 0, so this is equal to 0. Okay, so you can just jump into this step. This step is not really necessary. I just wrote it so you see what we're doing. So again, the step 1, take the Laplace of both sides. The next step is to use the formulas. So there's a formula for this thing. Maybe I'll write the formulas over here, then I'll erase them. So the Laplace of y, we're going to call that pitchfork y of s. Okay, the Laplace of y prime, that's going to be equal to s pitchfork y of s minus y of 0. I call this pitchfork y of s. I think it's just psi, but it looks like one of those pitchforks, like the guy who lives in the ocean, he has one of those. So this is the Laplace of y double prime. So I just have this one memorized, but notice there's a pattern. This is the first derivative. This is the first power. This is the first derivative. This is the 0th derivative. So it ends in one less derivative. So this is the second derivative. So it should start with an s squared pitchfork y of s. This is the second derivative. It should end in one less derivative. So this one's just going to be y of 0. And then this one is y prime because it has to end in one less derivative. That's how I memorize it. Is that the best way to memorize it? I have no idea. It's painful. This is a tough formula to know. So again, these are the formulas that we're going to use. Again, this is the second derivative. So it starts with s squared and it ends in one less derivative. Okay, so now let's go ahead and apply these formulas over here. So we have s squared pitchfork y of s minus sy of 0, so minus sy of 0, and it ends in one less derivative, so minus y prime of 0. Okay, minus y prime, and then plus 5, and then we have s pitchfork y of s minus y of 0, and then plus 4 pitchfork y of s, and that's equal to 0. I have no idea how hard this problem is going to be, so we will go slow. So again, these are the formulas you need. Do you need the one for the third derivative? No, it usually doesn't come up that much. I'll go ahead and write it for convenience. Let's see if we can figure it out. So y triple prime should be s cubed pitchfork y of s minus s squared, okay, minus s squared y of 0 minus s y prime of 0 minus y double prime of 0. See how I kind of, extrapolated that from the previous? So it's the third derivative, starts at 3, you see, and look, it ends at one less derivative. Second derivative, first derivative, 0th derivative, no derivative. Second derivative ends at one less derivative. First derivative, 0th derivative, no derivative. So that's the idea. Okay, so we're here now. So I'm going to erase this so we have some room. And let's go ahead and go to the next step. So again, step 1, you take the Laplace transform of both sides. You use the fact that it's linear. Now when you're here, you just simply apply the formulas and we get here. Now we actually invoke our initial conditions. We can actually use them. We impose them on the dE. So y of 0 is equal to 1. So that's going to be a minus s. So let's do that. So s squared pitchfork y of s minus s. Y prime of 0 is 0. So this is going to vanish. I'll write it minus 0 plus 5s pitchfork y of s. So 5s pitchfork y of s. Y of 0 is 1, so it'll be minus 5. So minus 5 plus 4 pitchfork y of s, and that's equal to 0. Be really careful in these problems. Always try to take your time. If you're able to take your time when you're doing these problems, you will get them right. The issue comes into play when there's like time constraints, and it's really easy to mess up here. One little mistake here and the whole thing is off. Let's see what we got. So I think we can factor out a pitchfork y from here, here, and here. So let's go ahead and do that. So we have pitchfork y of s So parentheses s squared plus 5s. So s squared plus 5s plus 4. Then you can add the s and add the 5 to the other sides. This will be s plus 5. Okay, good stuff. So again, we just basically pulled out the pitchfork y that gave us s squared plus 5s plus 4. Let's go ahead. Oh, so what do you do now? You solve for pitchfork y, right? So after you get here, you solve for pitchfork y. That's the next step. So you solve for pitchfork y. So let's divide by this. So we have pitchfork y of s is equal to s plus 5 divided by all of this. This is going to factor. Let's go ahead and factor it. It's going to be s plus 1, s plus 4 if I did that right. Let's check. S times s is s squared. Boom, there it is. 1 times 4 is 4. Boom, there it is. The inside is s, the outside is 4s. Inside plus outside is the middle. So s plus 4s is 5s. It works out perfectly. So this is what we have. So what are we even doing? We're solving this dE. So you take the Laplace transform, you impose your formulas, you solve for pitchfork y. Why? Well, here's why. Pitchfork y is actually equal to the Laplace transform of y. That was the definition. So we have the Laplace of y is equal to this. The question is to solve the dE. So the question is to find y. So it's really beautiful because now we have the Laplace of y, it's equal to this. So to find y, we just take the inverse Laplace of this. So that's why we were doing so many inverse Laplace problems before, because now to solve this dE, we're basically going to find the inverse Laplace of this expression. The Laplace takes y to this, so the inverse Laplace takes this back to y. Okay, I'm going to erase all of this and write this again over here, because to do this, we're going to use the partial fractions method. So let's erase, and then over here, I'm going to rewrite what we have. We have pitchfork y of s equal to this. So we have pitchfork y of s equal to s plus 5. So s plus 5 over, then we have s plus 1, s plus 4. So s plus 1, s plus 4. Beautiful stuff. Okay, so now we're going to use partial fractions. So whenever you have distinct linear factors like this, you can use the cover-up method. It's also called the Heaviside cover-up method, and I believe it's named after Oliver Heaviside, which was a physicist. This guy was a big-time smart person. So this is a over s plus 1 because it's a linear factor, plus b over s plus 4 because it's a linear factor. And we're going to use what's called the cover-up method. If you don't like the cover-up method, you can just use regular partial fractions. You would multiply both sides by this, but it's worth getting good at cover-up because it's so useful, it's so powerful. So to find a, what you do with the cover-up method is you go over here and you cover up what's under a. So s plus 1 is here, so you cover it up over here. And there's the question, there's two ways you can ask the question. Question 1 is, what makes this undefined? Well, -1. Or question 2 you can ask is, what makes the bottom 0? -1. They're the same thing. So whatever makes this 0, so -1. So you just plug in -1s here. So this will be -1 plus 5. This is working out nicer than expected. -1 plus 4. I had not done this problem. I had the problem written down, so I'm feeling like it's working out pretty nice. So 4, just don't want to mess up, 4 over 3. So there we are. So again, we cover this up and we plug in whatever makes that 0. So -1. Good stuff. Yeah, looks okay. Let's find b. So to find b, you cover up what's under b. So you go over here and cover it up. And you say, okay, what makes that 0? So -4. So it'll be -4 plus 5, -4 plus 1. Okay, so -4 plus 5. And then over here we have -4 plus 1. That's going to be 1 over -3. Let me check that. We covered this up and we plugged in -4s. Yep, it looks okay. It looks really good. So this is -1/3. So now we just take these, plug these back in and we finish. So a is 4/3. It goes up here, but you can put it in the front. That's what people do. So 4/3 times 1 over s plus 1. B is -1/3. It goes up top, but you can put it in the front. That's what people do. So this is -1/3, 1 over s plus 4. Okay, beautiful. This is pitchfork y. So y is the inverse Laplace of this. So y equals the inverse Laplace of all of this. The inverse Laplace transform is linear, so you can just take the inverse Laplace of each individual piece and pull out constants all day long. This is the inverse Laplace of 1 over s plus 1 minus 1/3 inverse Laplace of 1 over s plus 4. Really powerful technique, this method of solving dEs. So So now you can think of this as s minus negative 1. The formula we're going to be using repeatedly here is if you have the inverse Laplace of 1 over s minus a, that's equal to e to the at. So here it's s minus negative 1. This is going to give us an e to the negative t. So this will be 4/3 e to the negative t minus 1/3. And then same thing here, except it'll be e to the negative 4t. And that, my friends, is the final answer. We did it. We solved the differential equation using Laplace transforms. Honestly, I'll be honest, I thought this was going to be much, much harder, but it wasn't. So I am very happy about that. That's it. Take care.